Hey Frosty, are you ready to learn about Fibonacci and how it's related to the golden ratio? Come on, come on out. Let's get working on that. Oh, that dog is so lazy, let me tell you. Okay, well, Frosty's not going to be able to join us, but we can still work on the connection between Fibonacci and the golden ratio. Now, this won't take very long. This is actually quite simple, but I want to go over it. We know that the golden ratio solves the equation x squared is equal to x plus 1. Just like right there. Oh, that's not good. Let's try this. How's that? Better? Let's try it that way. Okay, we'll try it like that. Okay. Now, because the golden ratio satisfies this equation, and because the symbol that is specially reserved to describe the golden ratio is the Greek letter phi, we can replace this as phi squared is equal to phi plus 1. Okay, nothing new there. That's just the quadratic equation that the golden ratio solves. Okay, but just using this little piece of information alone, we can show that there is a connection between the golden ratio and the Fibonacci numbers. So, for example, if we take phi cubed, that's equal to phi times phi squared. But phi squared is just phi plus 1. So we can just put that in right like that. And then, since this phi times that is going to give phi squared, and that's just phi plus 1, we can write this as phi plus 1 plus phi. That phi times that gives this phi, and that is equal to 2 phi plus 1. Okay, now if we try this for phi 4, we'll see that we can find a pattern. This is equal to phi times phi cubed, but phi cubed is right over here, 2 phi plus 1. So we just put in the 2 phi plus 1. Then this phi times that phi is going to be phi squared, but that's just going to give us a phi plus 1. So we can write this as 2 times phi plus 1 plus this phi times that one gives another phi here. So that's equal to 2 phi plus phi, that's 3 phi plus 2. And we'll just do this for a few more until the pattern is really clear. To get phi cubed, phi to the 5th power, that's phi times phi to the 4th power, but that's just on the line above it, 3 phi plus 2. The phi squared is equal to phi plus 1, so that's 3 times phi plus 1, and then plus 2 phi. And then we've got 3 phi and 2 phi, that gives 5 phi plus 3. Okay? And then I'll just do one more. Phi 6 is equal to phi times phi to the 5th, but phi to the 5th is right over here. It's 5 phi plus 3. This phi times that phi gives us the only phi squared in the expression, which we reduce to phi plus 1. 5 times phi plus 1 plus 3 phi, that's equal to 8 phi plus 5. And then you can see that these are the Fibonacci numbers, 2, 3, 5, 8. And every time you multiply by another phi to get the extra power, it gives you another phi squared. in the term, but the phi squared just gives you another phi. So each time you, on the next one, it's going to be 13. You're going to have 13 of these phi's, and the 8, and you're going to get 8 over there. It's just a pattern. I'm not going to prove this. The idea is just to see the pattern. Now, the actual Fibonacci numbers are, that we had before are 1, 1, 2, 3, 5, 8, 13. And this is the first one. That's the second, third, fourth, fifth, sixth, seventh. So what we can see here, that this pattern is that phi to the nth. For example, when you have phi to the sixth, you have 8. But the number 8 is the sixth Fibonacci. So that's Fibonacci, the nth one, times phi, plus the Fibonacci, that's one less. So this is a formula for the nth power of the golden ratio. It's related to the golden ratio itself and the Fibonacci, the nth Fibonacci number, and the Fibonacci number preceding the nth Fibonacci number. So this is a little relationship that can be useful. It's nothing, I don't think there's anything really deep here. It just shows that because phi is a solution of this algebraic expression, which is relatively simple, that when you calculate that to the multiple powers, you do end up adding numbers in a way that produces the same sequence as the Fibonacci sequence. And this is a relationship between them. Okay? That's all on this one.